Welcome to Chapter 9, Stoichiometry. Stoichiometry might be one of the best chapters of the entire year. I don't know, maybe I say that with every chapter, but this really is the meat and potatoes of chemistry. This will combine everything we've done all third quarter. It's great. It's going to take a little practice and a little patience on your behalf, but I think you're going to love it, as I hope you do. Stoichiometry is a study of all quantitative aspects of a chemical reaction. So in the last chapter, it was all qualitative. We didn't measure anything in the lab. We just recorded our observations. Oh, cool, we have a yellow precipitate. Now we're going to want to know how much yellow precipitate. It becomes more quantitative when we look at stoichiometry. We're still going to need balanced equations, and we are going to be obsessed with the ratio in the balanced equation. For example, an easy reaction. How about, I think we kind of mentioned this one in the last chapter. Hydrogen reacts with oxygen gas to produce water. So in the last chapter, when we were really just focusing on balancing the equation, we often list those coefficients as a ratio of atoms or molecules. So we could read this as 2 molecules of hydrogen plus 1 molecule of oxygen, producing 2 molecules of water. And there's absolutely nothing wrong with that. However, if we want to try to go in the lab and run this reaction, that's not realistic. I can't go in the lab and find 2 molecules of hydrogen, 1 molecule of oxygen, and smush them together and make 2 water molecules. That's just not going to happen. We need to work with larger quantities. So instead of reading it as a ratio of atoms or molecules, we're going to use the mole. The mole is back, yes. So if I read these coefficients as a ratio of moles, we could say 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. Now, I guess that's still a little tricky if you were going to run this in the lab. In the lab, the electronic balances don't measure in moles. So could we use moles to compare a different unit? How about like atoms or molecules, just on a larger scale? If I had 1 mole of oxygen, that would be 6.02 times 10 to the 23rd molecules. 2 moles would be double. I could read it as 12.04 times 10 to the 23rd. Or I could say 1.204 times 10 to the 24th molecules of hydrogen. And if I had 2 moles of water, I could do the same. 1.204 times 10 to the 24th molecules of water. So I kept the ratio consistent. When particles react in a chemical reaction, they react as a ratio of atoms or molecules. I need 2 molecules of hydrogen for every 1 molecule of oxygen. And we just said that that's unrealistic. It's way too small. So let's amp it up a little bit and use larger ratios. But we still kept the original ratio consistent. It's still a 2:1:2 ratio of particles. I still have twice as many molecules of hydrogen as oxygen. For every 1 molecule of oxygen, I produce twice as many molecules of water. So I kept that ratio consistent. But again, we run into a little trouble because in the lab, I can't count that high. Well, I guess nowhere can I count to 10 to the 23rd power. Realistically, in the lab, we're going to want to measure in grams. We're going to want to use the electronic balance in grams. So could I find the mass of 2 moles of hydrogen gas? So hydrogen is about 1 gram per mole. H2 diatomic would be about 2 grams. 2 times 2, about 4 grams of hydrogen. Could I go in the lab and measure 4 grams of hydrogen? Absolutely, yes. 1 mole of O2 oxygen, 16 times 2, 32 grams. Sure, that's a reasonable number. I can measure 32 grams of oxygen in the lab. Water. Each of the hydrogens have a mass of about 1. The oxygen is about 16. So if we say 2 times 18 grams, 2 moles of water would be about 36 grams. I could measure that in the lab. It'd be about 36 milliliters. That is what we'll want to do in the lab. We're going to use the ratio from the balanced equation as a ratio of moles. It's still a ratio of particles. But then to make our measurements in the lab, we'll turn moles into grams. And look at this. The law of conservation of mass still applies. If I have a total of 36 grams on the reactant side, bingo, we have 36 grams of product. It's magic, huh? The law of conservation of mass still wins. Now here's the only thing that does not fly. We cannot directly use those coefficients as a ratio of mass. So you cannot say 2 grams of hydrogen plus 1 gram of oxygen produces 2 grams of water. That's the only one here that doesn't work. Sad face. This one doesn't work. The ratio in the balanced equation is not a ratio of grams. It's a ratio of particles. Now, indirectly, we can use the mole as a ratio of particles, and then we can switch moles into grams. But notice that, like, the mass of hydrogen and oxygen is not 2 to 1. Oxygen atoms are like 16 times more massive than an atom of hydrogen. See, you can't use the coefficients as a ratio of grams. But yes, you can get grams from moles. So when we go on through this stoichiometry, we'll be obsessed with balancing the equations, which we just did in the last chapter, so that's going to be great. And then we're going to be obsessed with that mole ratio, the ratio of coefficients from the balanced equation. We'll use them to get grams that we can measure in the lab.